at ASU in the Saltwater Center under Dr. Kaushal Rege and my mentor, Mr. Matthew Christensen. Our project this year is titled Reducing Cancer Cell Apoptosis Using Polymer-Mediated Gene Delivery. Now, as you know, cancer is a growing problem in today's society, and there are many ways that have been developed to fight cancer. However, none of them are 100% effective, and some of you have their drawbacks. And with every single one, cancer has the ability to come back again. That's why several new methods are being researched and developed. One of these methods is known as gene delivery, which is the use of certain vectors, you could say, to transport DNA into the nucleus of a cell, a cancer cell, which will cause the cells to undergo apoptosis, or programmed cell death. There are two types of gene delivery. There is viral gene delivery and non-viral gene delivery. Viral gene delivery is exactly as it sounds. It's the use of viruses to transport that plasmid DNA into the cells. That has its drawbacks as well, such as high cytotoxicity. It can kill what we don't want it to kill. Some viruses are very unstable, and some of them just don't get in very well. That is why non-viral gene delivery is being researched. And of the several different types of non-viral gene delivery, I focus on polymer-mediated gene delivery. Polymer-mediated gene delivery is the use of polymers, which are long chains of polyamines and diglycine ethers, formed together all a long chain, and is formed with a plasmid DNA that occurs in certain bacteria and has a specific purpose. Now, polyplex is the formation of that polymer and plasmid into just one form. My problem was, how well do cancer therapeutic plasmids RB1 and P21 transfect into the MB49 bladder cancer cells and 22RB1 prostate cancer cells when formed with polymers perimyzine glycerol diglycerol, or PGG? And I want to know, what is their effects on the levels of cell apoptosis? My hypothesis was that the delivery of the plasmids RB1 and P21 would lead to a greater loss of cell viability when compared to the non-expressing plasmid PGL 4.50. My null hypothesis was that the delivery of the plasmids RB1 and P21 will lead to no changes in cell viability in comparison to non-expressing plasmid. This here is the P53 pathway. P53 is a plasmid that is commonly used in labs today. It has several functions. It can either A, lead to apoptosis, or B, can activate these two other plasmids that are used. P21, which inhibits cyclin E or cyclin E1, causing cell arrest in the G1 S phase of mitosis, so the cell's life cycle. It will stop right in that phase. It can also activate RB1, which will inhibit G2F, which also causes G1 S arrest. So for my procedures, what I did was called a transfection. I would plate several cells in a 24-well culture plate at about 50,000 cells per well. The next day, I would replace the media that was in there with fresh serum-free media, so it didn't have all the nutrients that the cells needed to multiply. I would form the polyplexes with polymer and plasmids for about 20 minutes. I would stick them in a little tiny tube and let them sit there for 20 minutes, and then I would transfer those polyplexes to the media and let it sit for about 2 to 3 days in a 37-degree incubator at 5% carbon dioxide. Now, during this transfection, here's what happens. The polymer up to the left will form with the plasmid to form a polyplex, which is down at the bottom left. Polyplex will enter the cell and what is called the lysosome. It will escape the lysosome. The plasmid will go out of the cell. The polymer will go out of the cell. The plasmid will transfer into the nucleus, little blue circles with the squiggly inside of it, and it will replace the little squiggly, which is the cell's DNA, and cause cell apoptosis, or in this case, cell arrest. Now, to determine whether the transfection worked, I had to do what's called an MTT proliferation assay. Now, in dim light, because the reagents that I'm using are light sensitive, I would add 20 microliters of what's called MTT reagent to each well and cover with aluminum foil and let it sit for about 4 hours. After that 4 hours, I would add 100 microliters of detergent and let it sit for at least 2 hours, sometimes going overnight. Now, what the MTT reagent does is, on the left you see the transfection plate. The media is all pink. It's a big bright pink, and it has all the cells, and they're all alive. On the right, you see it turn to a deep violet. That's because of the MTT reagent. What it does is the metabolizing cells, the cells that don't have plasmid DNA in them and are still going through their processes, they are producing what's called formosand crystals. They're a deep violet crystal that are insoluble in media. They won't dissolve in the media, causing the media to go to a deep violet. That is why I add the detergent, so I can break the cells apart and cause those formosand crystals to be soluble again. So after I added that, I would desolubilize formosand crystals in each well. I have what's called a pipette, and I would be mixing up each and every single well for several minutes at a time. I would transfer to another culture plate that has 96 wells instead of 24. I would transfer each sample in duplicate. I would take the plate to an IMARC plate reader and read them at 570 nanometers. So I would shine a light at 570 nanometers, and I would take the absorbance of the sample, the light from the sample, and I would export all my data to Microsoft Excel. I would then perform volume corrections to make sure that all my results were consistent, and I would take into account the evaporation of the media while it's incubating. What I found was that the addition of the plasmids did cause a slight decrease in cell viability when compared to the control plasmid. Control plasmid being the pinkish column that you see in each one, and the other plasmids, the RB1 and P21 being the two columns next to it. Now, what I found was that even in those slight decreases, my data was not statistically significant. When I performed a two-tailed t-test, which determines the p-values, which state what is the likelihood that the results that I have were obtained by coincidence? How likely is it this happened by chance? What I was looking for was a p-value with p-value under 0.05. Well, the only two conditions to have done that were the 200 nanogram P21 in both conditions. Everything else was between 0.08 and 0.74, making all that data statistically insignificant. To determine why this was insignificant, I decided to do polymer screening. Now what that is, I would form my polyplexes in a small little cuvette, and I would take them to a dynamic light scattering machine, which what that does is it uses a ray of light and it will shine it through the sample of polyplexes, and the machine will measure the diffraction of light to determine the size of the polyplex. What I found is that very few were in the target range that I was looking for. The target range that I'm looking for is underneath 250 nanometers. That is because the pores of the cells are very small, and if the polyplexes are too big to fit through the pores of the cells, they can't get through the nucleus. Therefore, they will not transfect the cells, and there will be no cell arrest, making the transfection a failure. There were very few that actually hit where I wanted. There was the 25-to-1 PGDGE, the 50-to-1 PG1.5 lipopolymer, and the 50-to-1 AG1.5 lipopolymer. The rest, however, were too large to fit into the cells. So in discussion, what I found was that most of my data was insignificant, largely due to the polyplexes being too large. Now, there are also been errors in my MTT assay, such as clumps of crystals. When you're resolubilizing the formosand crystals, you can't solubilize them all the way, and there will always be little purple clumps in the solution, making it to where the absorbance measured can be thrown off. I also may have done incorrect volume corrections, but that would have been kept to a very slight margin due to the constant oversee by my mentor. In future applications, I would like to use the results of my experiment to maybe progress further into using different types of transfections. I could maybe perform using a double transfection using one of the two plasmids that I use today, and maybe doing a second one after that using a plasmid, such as the actual P53 plasmid, to maybe finish off what the other two plasmids could have done. This could also be used for polymer screening or plasmid screening to see how well do these plasmids work with this polymer. What if they work better with this polymer, with this cell line? Maybe this cell line won't activate this plasmid. So I would like to test different plasmids, different polymers from different cell lines to see what is the best combination and what is more useful for this cell line of cancer to help with others. I would like to give special recognition to my mentor, Mr. Matt Christensen. He has helped me throughout my entire science fair project and has put up with me coming in a lot. I would also like to recognize my PI in my lab, Dr. Kaushal Regate, for letting me use his lab and helping me get the resources that I need to perform my science experiment. I would like to thank Mrs. Amanda Grimes, the biotechnology coordinator, who has given me the opportunity to have this internship and has helped me with ideas and going through my project and making sure I don't go completely insane. I would also like to thank my parents, Mr. Jennifer Glenn and Mr. Everett Glenn Jr. They have put up with me not being at home and having to be out all the time. They've helped giving me money to use the light rail to go to ASU constantly, and they've put up with a lot of my just psychotic freakouts over the course of the past 2 years. Are there any questions?